Okay, so today we're going to talk about piecewise functions. So piecewise functions are functions that are made up of different pieces of graphs, so different types of functions that are combined together in a single graph to create one piecewise function. So functions that have different definitions on different parts of their domain are called piecewise. Piecewise functions. If all the pieces are linear, then the function is called linear piecewise. So to evaluate a piecewise function, you just need to look at which piece of the function that you're going to plug a particular value of x into. So what portion of the domain does that particular x value fall into, so that we can evaluate f of x. Okay, so looking at our first graph that we have here, this piecewise function is actually made up of two separate functions. We can see that the function on the left, I'll highlight that in yellow here, is actually a quadratic function. And then the piece of the graph on the right, highlighted in green, is a linear function. So I take this quadratic function and this linear function, I put them together, I combine them to form a single piecewise function. But depending on what I'm trying to evaluate, if I've got a particular x value, I need to know, do I put that x value into the quadratic function to find the appropriate value for y, or do I put it into the linear function to find the appropriate value for y? So for my quadratic function here, my function is actually f of x equals negative x squared plus 3. And then the linear function is f of x equals x minus 3. So for example, let's say I want to evaluate when x is equal to 4. So that would be here. X is equal to 4. Well, I can see that falls in the domain of the linear portion of the graph. And so when x is equal to 4, I would evaluate that here in the linear function, as opposed to if I was looking to evaluate when x is equal to maybe -1. -1 is here on the graph. I can see that falls into the domain of the quadratic function, and so I would substitute -1 into the formula for the quadratic function to find the corresponding y value. Okay, so let's go through, answer the questions over here on the left. First question we're going to answer is, what is the domain in interval notation? When I'm looking at the domain, I'm looking at the domain for the graph as a whole, even though that this piecewise function is made up of a variety of functions. We look at the domain for as a whole. Okay, so I can see that the graph starts from negative infinity here. This goes on forever to the left. So I'll have negative infinity, and I'll track along, and I can see I have a point here where it changes from a quadratic function to a linear function, which is fine, and my domain continues. And then finally, my largest x value is here at 7. So my domain is negative infinity to 7. 7 has a closed circle, so I'm going to use a bracket to show that 7 is included. Now I want to look at the range. And so same thing, look at your y values, looking at the graph as a whole. I can see that my smallest y value would be at negative infinity. And then it comes up the graph to where I get here, and then you can see my largest y value is actually here at 4. That corresponds with this point on the graph. So my range is from negative infinity to 4. Again, I'm going to use a bracket because that's a closed circle. Okay, now I want to do some evaluations of some points. I'll clean this up a little bit. Okay, so first point I want to look at is f of -1. So f of -1, that's here on the graph, and the corresponding y value looks like it's here at 2. So f of -1 is 2. F of 8. So f of 8 is over here on the graph. I'm looking for the corresponding y value, and you can see there's not one. And so this would be DNE, or does not exist. Well, this makes sense because remember, our domain here was from negative infinity to 7. So 8 is actually outside the domain. So it makes sense that there's no corresponding point on the graph because that's not even within the domain of the function. All right, for number 5, if f of x equals -1, so that's the same as if we say if y equals -1, then we want to know what the corresponding x values are. Well, y would be -1 here, and I usually just sort of go across and draw a dotted line and just see where do I intersect the graph. And you can see you would intersect the graph at 2 points, here at -2, and then here at +2. So the corresponding x values when y is -1, x is equal to -2, and x is equal to +2. Okay, number 6, is the graph 1 to 1? So remember, in order to be 1 to 1, you have to pass the horizontal line test. Well, I can see that this graph does not pass the horizontal line test. Okay, I can go ahead and draw a line through here and I would intersect in 3 points. So obviously it fails the horizontal line test. So then your answer here is no, it's not 1 to 1. And then of course always tell me why, and that's because it fails the horizontal line test. Okay, number 7, intervals where it is increasing. So remember, think about that as a roller coaster. We read a graph from left to right, just like we read a book from left to right. So I'm looking for where the graph is increasing. So increasing here. So the interval where it's increasing, that's a subset of the domain. So that would be from -infinity to 0. And then it's also increasing here from 2 to 7. So union 2 to 7. Now I've used parentheses for both of these intervals because remember the way that we define increasing and decreasing requires that we use parentheses. So you can refer back to your notes on our function work a couple days ago to look that up if you need to. Number 8, interval where the function is decreasing. So now I'm looking for, as I read from left to right, where's the graph decreasing? Like where are you going down that roller coaster hill? And that region would be from 0 to 2. Where is a local maximum? Number 9. So local maximum is a point that's higher than every other point around it. That's what it means to be a local maximum. So I have a local maximum here. Now this represents a coordinate point. So this is an XY coordinate. So that would be at 0, 3. Okay. It's also where the graph changes. This triangle is shorthand for changes. Changes from increasing to decreasing. Okay, and so you can see on the left it was increasing and then it changed to decreasing. So that's my local maximum. My local minimum is where it's lower than every other point around it. So I have a local minimum here. Okay, that point is 2, -1, and that is where it changes from decreasing to increasing. Okay. Number 10, absolute maximum. So absolute maximum and absolute minimums are over the entire domain versus just the points around it. So the absolute maximum is the point that's higher than every other point on the graph. That would be here. That's my absolute maximum. That point is at 7, 4. And then the absolute minimum, there actually is not an absolute minimum. You can put D and E or none. And that's because the graph goes to -infinity. And so there is no way to quantify what the lowest point is. What point is lower than every other point on the graph goes down to -infinity. And so my answer for absolute minimum there is none. Okay, so that's our first graph. Second graph here, you can see you've got 3 pieces now of my piecewise function. The one on the far left looks like it might be part of a quadratic again. The one in the middle could be part of a quadratic, might be part of an exponential. And then the graph on the far right could also be maybe part of a quadratic, part of an exponential, get that little bit of a bend, could be pieces of a polynomial. We really don't know. And it doesn't matter because we don't need to know the functions here. We just need to know, we need to be able to read the graph, identify domain and range, and then answer some other questions just based on the graph itself. So what I want you to do is I want you to pause here, go through, answer these 10 questions. Let's see how you do. And then when you come back, I'll give a quick explanation for each one. Okay, so here's your answers for the second portion of the graph. For domain, you should have -4 to 0 with brackets, union 1 to 4 with parentheses, union 4 to 8 with a bracket. So when I'm looking at domain, remember I'm looking at the x values. So from -4. I use a bracket with that because it's a closed circle. So I've got x values that go from -4 to 0. Again, closed circle, so that'll be a bracket. And then I don't have any x values between 0 and 1. So I'll have a union symbol there indicating that break. And then at 1, I have an open circle. So that's the reason that I have my parenthesis there at 1. And then all the way across to 4, again, open circle. Now it picks up at the bottom at the third graph, the graph that's most to the right picks up down here at 4 as well, but also has an open circle. So there is no x value associated with this graph when x is equal to 4, okay? And that's the reason we use parentheses for both of those. And then finally, the x values will go from 4 until you get to 8, and down here at 8, I have a closed circle, so I need to use a bracket. Okay, so that's my domain. Range should be from -12 to 9, and that's because my smallest y value down here is at -12. I use a bracket because that is a closed circle, and then my y values come all the way up to where this bottom piece of the graph ends, and I can see it comes to 0, but then I just jump over here to the next portion of the graph, so I have y values here at 0, all the way up to 4, and then I just jump across here to this portion of the graph, and I have y values from 4 all the way up to 9. But because this is an open circle, I'll use a parenthesis on 9. So I have y values on this graph from -12 to 9. Even though you have to jump from one piece of the graph to the other, there are y values for all those values between -12 and 9. So now we're ready to look at number 3 for f of -4. So when x is -4, we want to find the corresponding y value, and that is this point here, which y would be 0. F of 8 is -12. So when x is 8 here, come down and you'll find the corresponding y value at -12. Number 5, if f of x equals 0, so that's the same as saying if y equals 0, we want to know what the corresponding x value would be. Well, y is 0 here at the x-axis. So come across, I'm actually going to erase some of these marks just to make sure this is really easy to read. Sometimes it gets a little covered up here. Okay, so when y is equal to 0, we want to know what that corresponding value is. So again, I normally come across here and make marks and just see where do I hit the graph. So here x is equal to 4. Now this is an open circle, so I don't want to include that value. So I just want to include the value where x is equal to -4. Number 6, is it 1-to-1? The answer is no, because it fails the horizontal line test. And so I can prove that by just doing a dotted line like this and seeing that you intersect in more than one place. And then number 7, intervals where it's increasing. So this graph is increasing here from -4 to 0, and then increasing again. This is when x is 1, from 1 to 4. Again, make sure that you have parentheses around your answer here, because increasing, decreasing are always parentheses. Intervals where it's decreasing, so it's decreasing here from 4 to, that's 8. Okay, remember, increasing, decreasing are subsets of the domain. So these represent one x value to another x value. So subsets of the domain. They are from x1 to whatever x2 is. Okay. Number 9, where is the local maximum? So is there a point on the graph that's higher than the other points around it? Is there a point where it changes from increasing to decreasing? And the answer is no, okay? You may have said that this point here was a local maximum, but it's not. It doesn't change on the graph from increasing to decreasing. It's increasing on the left side, but then it ends. And so then you have a break in the graph. So no for that one. Local minimum, same thing. There's no place where it changes from decreasing to increasing. Number 10, absolute maximum. So over the entire domain of the graph, is there a point that's higher than every other point? The answer is no, there's none, because this is an open circle. If that had been a closed circle, that would have been your absolute maximum. And then absolute minimum is down here at 8, -12, and that's because that was a closed circle. And so that's the reason we were able to mark that as your absolute minimum. Okay, so we've got a third example here. So for this one, we're looking at a piecewise function again. This one is made up of 3 separate pieces or 3 separate functions that create the entirety of the piecewise function. The graph on the far left is linear. The graph in the middle is a quadratic, and then the graph on the far right is also linear. The difference between the 2 linear functions, the one on the left is actually a constant, and the one on the right is what we think of as more of a linear function. So for this particular function, again, I'd like you to pause the video, work through it, answer the questions that are here, and then come back and you can check your solutions, and I'll just go through a brief discussion for those. Okay, so here are your solutions. So the domain, you should have negative infinity to 0, union 0 to infinity. This one was just a little bit tricky. It can be hard to read on the graph. This is actually an open circle here at 0, 0. So if you didn't notice that that was an open circle, you may have missed your domain there. But other than that, if we read from left to right, this is considered to be an arrow to the far left and comes all the way across. And then the x values pick up again down here on this portion of the graph. Does not exist at 0, 0. X values continue across. And then we just sort of have to jump down. The value here is 2. So let's see if we can mark this. This is 2 here on the graph. And then the graph continues down here to infinity. So the only place where the x values don't exist is at that point 0, 0. The range, you should have negative infinity to negative 1, union 0 to 4. And that's because the lowest y value on the graph here is from negative infinity. And then, of course, we read up until we get to a point here at negative 1 where the graph is an open circle, so we don't want to include that. There are no y values between negative 1 and 0. 0, again, of course, is an open circle, but the points pick up just on the other side of 0, and then the y values go all the way up to 4, which is the largest y value. F of negative 4, you should have 3. F of 2 is equal to 4. If f of x equals 0, so that's the same as saying if y equals 0, then x does not exist. And that's because if we look at our value here, where y is equal to 0, of course, that's the x-axis coming across. And then the only x value that looks like it might be associated with it here is here when x is 0, but again, that's an open circle. And so there's actually not a point on the graph there. So when y equals 0, there is no associated x value on the graph. So that's why it does not exist. Is it 1 to 1? No, it's not 1 to 1. It fails the horizontal line test. There's lots of values where it fails the test, but anywhere in this region here where you would cross and hit the graph in multiple places. For 17, the interval where it is increasing, let me see if I can get some of this off here, where it's increasing is this region here, and that's from 0 to 2. Remember, these are x values. It's a subset of your domain. So from 0 to 2, it's increasing. Where it's decreasing is from negative 1 to 0, and then also from 2 to infinity. The graph is decreasing. Where the graph is constant, we have an area where it's constant from negative infinity to negative 1. This is an arrow here at the end. I kind of got cut off on my graph there a bit. Local maximum, there is no local maximum. There's no place where the graph changes from increasing to decreasing. Local minimum, none. Now this was a little confusing. None. The only reason that it's none here is because the graph doesn't exist at 0, 0. Normally your local minimum is where it changes from decreasing to increasing, and so typically you would have a local minimum here at this point 0, 0, but because that's an open circle, it doesn't exist. Absolute maximum is at 2, 4. That's your highest point on the graph, so that's up here. Absolute maximum. Absolute minimum, again, none, and that's because my value as you move across, as you move down, this goes to negative infinity, and so you can't quantify any particular point there. Now, one question you may have is, for my absolute maximum here, why is that also not an absolute or a local maximum? And it's not a local maximum because if you remember, local maximum and local minimums cannot occur at endpoints, and it has to do with the way those are defined. So we never have a local max or a local minimum at an endpoint. Okay, so hopefully you did well on that. So moving on along, okay. So when we're evaluating piecewise functions, if we're going to evaluate a piecewise function, we have to know which piece, that's my blank here, which piece of the function to substitute a particular value of x into, so that we can evaluate and figure out what our f of x or our output value will be. So you'll ask yourself, which interval of the domain does the x fall in? And then how is the function defined there? So for my example down below, instead of a graph, we have of x equals 2x, and that is for x values that are less than 0. It equals x plus 3 for x values that are greater than or equal to 0 but less than 2. And then finally, we'll use the function x minus 3 squared for x values that are greater than or equal to 2. So if you tell me where you want to evaluate, what you want your x value to be, then I know which function to put it into. So for example, my first question here is to evaluate g of 0. So that would fall in this second interval of the domain where x is greater than or equal to 0 but less than 2. So that means I'm going to use the function x plus 3 to evaluate. And so I'll put in 0 for x. It'll be 0 plus 3, which of course equals 3. So that means there's a point on this graph at the point 0, 3. Okay, I'll let you finish the rest of these. And then from here, that wraps up this video. Start your next video, and it'll have the solutions for this particular problem along with the rest of your notes.